This is a farm near the small town of Lumberton, North Carolina. The crop from these seeds won't be ready to harvest for at least 20 years. It's not corn or wheat, soybean or cotton being planted here. It's trees. These are the seeds of the loblolly pine tree. The loblolly pine is now a major agricultural crop throughout the southeastern United States. Last year alone, more than 600 million tree seedlings were planted in the South. On this field, 2.5 million pines are off to a healthy start. If they all make it, these seedlings will be the newspapers and writing pads, facial tissues and cardboard boxes for the year 2000. The question this program wants to ask is, are trees really a renewable resource? A tree crop needs room to grow, so after the first season, these trees must be transplanted. This first cutting loosens the entire tree. Care is taken while handling these trees to prevent damage to the life-supporting roots. Abandoned farms and cotton fields, the soil worn out from repeated agricultural use, are being turned into woodlands. The trees are replanted well-spaced, almost 600 to the acre. These pines will begin to reach harvestable size in 25 years. Many of today's mature forests in the South are actually man-made tree plantations, started years ago by some far-sighted landowners. It was a newsworthy event. By the early 1900s, most of the South's native forests were completely cut to the ground. Lumber towns came and went. Their average lifespan was 20 years. They disappeared when the wood ran out. Some paper mill owners wanted their investments to last longer, and so they began farming trees. The mild winters and hot, humid summers in the South were ideal conditions, providing a natural greenhouse for the young trees. During the 1930s depression, the federal government employed thousands of people in reforestation programs, and growing trees as a crop became big business. Farming techniques adapted surprisingly well to cultivating trees, and the flat southern plains were on their way to becoming new forests. But the need for wood grew even quicker than these fast-growing pines. Lumbermen felt drastic steps were needed to meet the increasing demand. This is Professor Bruce Zobel of North Carolina State University and Jim Dyness of Federal Paperboard Company. And this forest is one of Federal Paper's tree plantations. The target of this hunt is a mature branch of the tallest, the straightest, the fastest-growing, most disease-resistant pine tree Bruce Zobel could find. And why? Because Zobel has been trying to create an entire forest of genetically superior trees. This idea began in 1951 for very different reasons. Zobel was attempting to grow pine trees in an overly dry stretch of West Texas. He needed a technique to get seeds. He found some pines that had survived well in a recent drought, and with a few branches from these trees, Zobel began an experiment which would change the face of the southern forest. Plant grafting was a well-known agricultural technique then, but it had never worked on pine trees. Taking a cutting from the mature branch, Zobel tried clipping off most of the needles to slow the growth. He then formed two smooth surfaces on the limb in the shape of a V, being very careful never to touch the freshly cut areas. The key was how well these surfaces matched the cut in the root base. By wrapping them tightly together, he kept all the moisture flowing through the graft. And what was he trying to achieve back then?
Well, when we first started this type of work, we had to get some way to make large amounts of improved genetic seed, and it takes 15 years or so before a tree will produce seed as a seedling. But by grafting, we bring the parts of a mature tree down to the ground, and we get seed within 3 or 4 or 5 years. But when I first started, I wasn't even sure we could graft. In fact, I was told that we couldn't graft.
But Zobel found that if he picked the right root base, it worked. And he began grafting whole orchards of superior branches from drought-resistant trees. The success of this grafting led not only to drought-resistant seeds, but to a whole new idea, super trees. Why not make ordinary trees better by growing only specially chosen stock? This graft was made in 1961, and today is part of a seed orchard producing some 12 million super seeds each year. These are all grafted trees made from selected branches gathered throughout North Carolina. The super seeds will grow an entire crop of trees like their superior parents. But appearances aren't all that count. Each tree must be tested to make sure it's truly genetically superior. Inside the bag is a tiny female pine flower, the beginnings of a pine cone. Here it's not left to the birds and the bees. Instead, the cone is fertilized by hand with pollen taken from another superior tree. When the cone matures, test plantings are made to determine which trees actually produce better genetic traits, the straightness, the fast growth. It's from these truly superior trees that cones are eventually clipped and seeds collected for widespread planting. There are now nearly 250 super tree seed orchards throughout the South, and almost all the seeds being planted today come from this superior stock. What are the potential gains with super trees? Professor Zobel.
In the group that I work with, we plant about 300 million trees every year. This is equivalent to about 400,000 acres every year. So that we feel if we can get even a small gain, 5 to 10%, or we're now finding that we can get 10 to 20% in the first generation, that this is going to be extremely valuable in producing the amount of natural resource that we need.
At least 10% more wood, just by using the right seeds. The first crop of super trees are only now being harvested. This is the Paul Bunyan of the 1970s. With one bite, the trees are snipped off right at the ground. The loblolly pine is ideal for this kind of harvesting technique because of its thin trunk. Most of the wood cut in the South is earmarked for one purpose, pulp, for paper. Each Sunday edition of the New York Times requires 153 acres of this kind of tree. The paper sacks, napkins, paper cups, and packing used by McDonald's gobbles up 315 square miles of trees every year. We used over 100 million tons of pulp wood last year. If we hadn't started planting trees 50 years ago, we could not meet today's demand for paper. At current consumption rates, that demand is predicted to double in the next 30 years. It's hoped the super trees being planted today will meet that future demand. But that's not half the story of the nation's wood supply. Still, the first and foremost use is wood in its traditional form, as lumber. These huge logs will be tomorrow's houses and apartments, construction and building materials. Most lumber is made from big trees, and big trees are old trees. And where does one find old trees? The magnificent Pacific Northwest, Washington, the Oregon Cascade Mountains, Northern California. On these mountainous slopes and in the fertile valleys grow most of the last grand old stands of timber left in the United States. The North American continent once had the richest timber stands in the world. When the first settlers arrived, nearly 2/3 of the country was covered with trees. It was plentiful and free, a natural resource to be used. The U.S. still has over 500 million acres of commercial forest land. During the last 2 centuries, ownership of this timberland has changed hands many times. And today, the owners fall into 3 major categories. 13% of the forests are owned by the forest industry, the large corporations like Weyerhaeuser, Crown-Zellerbach, International Paper. Another 59% is owned by over 4 million small landowners, farmers, vacationers, very small timber operators. And the rest is owned by governments, local, state, and federal. Most of this is in the national forests, supervised by the U.S. Forest Service. In contrast to the national parks, the national forests were established partly to provide timber for the nation. The history of the lumber industry in the United States was initially cut out and get out. They started in Maine and then moved through the Lake States to the south, and then on across the country to the Rocky Mountains, and by 1910, the West. There never seemed a limit to this resource. There were always more trees just over the next hill. But when one gets to the Pacific Northwest and reaches the sea, there are no more hills to go over. These are the trees left to cut. Some of these trees have been growing for well over 400 years. Time is what trees need most of all. Time to grow, time to take in nutrients from the soil, to soak in energy from the sun and moisture from the rain. Time to mature and produce seeds and more trees and develop into a whole forest. The entire forest has taken many generations to develop. In the young forest, there are many species, but as time passes, this will gradually change. 1 or 2 species will tend to dominate. Not only must a logger wait for trees to grow before they can be harvested, he must wait for the forest itself to evolve into the species he wants. Professor Henry Horn of Princeton University has been trying to study just how a forest changes. Using a homemade light meter, Horn carefully measures the amount of sun falling on each small tree. He compares the annual growth with how much light is blocked out by the trees overhead. From these many readings, he's beginning to understand why certain species come and go.
All of the trees here are competing for light in one way or another. This old apple tree moved into an open field at about the same time that the white birches around it did. However, the apple tree, although it spread out all over the herbs that were underneath it, was unable to grow to the kind of height that the white birches have grown to. The white birches, of course, will succumb to the trees that are in the understory, like the beech here or this sugar maple, which are able to endure shade that the white birch couldn't stand.
And slowly, one species after another takes over a forest and dominates, but only for a period of time. At some stages in the forest history, the woods seem almost devoid of life. The foliage at the top of these white pines has so completely blocked out the sun, no other species can get a start.
This tree is about 35 years old or so. It's a white pine. From all the dead branches around, you would think that this is a fairly non-productive forest. These dead branches at the bottom indicate that the white pine is unable to grow successfully in its own shade.
But in fact, the tops of the trees are growing fine. The tree isn't dead at all.
The needles up at the top are growing quite well, and the tree is very productive. It's putting on quite a bit of wood. It's just the kind of tree that one would like to manage for production.
And indeed, that's just the type of tree which provides much of today's lumber. This is a 90-year-old Douglas fir growing in northern Oregon. It grows in much the same way as the white pine, reaching tall and straight towards the sky. Douglas fir trees have been measured well over 300 feet tall. This species produces more timber than any other. Following a fire, the Douglas fir is the first tree to reappear, and with moist conditions and moderate climate, it matures rapidly, growing more than 2 feet each year until it's well past 50 years old. Throughout the coastal Northwest, it occurs in vast, almost pure, even-aged stands. According to forest industry estimates, an average family consumes a tree this size in wood products each year. Actually, this tree is relatively small. Other species are also cut for lumber in the Northwest. These are even older trees: the western hemlock, the cedar, the fir, the redwood. They're 400, 500, 600 years old. As young trees, they thrived in the shade, until after several hundred years, they overtopped trees like the Douglas fir and grew to this size. This tree was a seedling long before Columbus first landed. Trees that have taken this long to grow will take that long again to return. That's why old trees are just like coal and oil. They are a mined resource. Once exhausted, they are, practically speaking, not renewable. It's not only man that has been depleting this resource. For centuries, nature has been destroying tens of millions of acres of old forests every year. Containing fires to protect and stretch the valuable wood resource was probably the earliest effort at forest management. Soon after the U.S. Forest Service was formed in 1898, forest fire prevention was in full swing. Forest land lost to fire was dramatically reduced. Today, despite our best efforts, natural fire still claims almost 4 million acres of trees each year, enough wood to build 500,000 new homes. Further efforts were needed to extend the resource. Beginning in the late 1940s, forest stands were thinned of the weaker trees, leaving more room for the better trees to grow. And what effect does this thinning have? The manager of one of Crown Zellerbach's managed forests, Frank Deckenbach.
Here is an example of a cross-section of a tree showing the results of thinning. You'll notice that there are wider growth rings in the outer diameter of this tree. And in this cross-section, you can see the slower growth in the early years. And then about 15 years ago, the timber was thinned, allowing those that remain to grow faster, and all of the nutrients and the sunshine and the productivity of the soil to go into the remaining trees, creating more growth on fewer trees.
Its estimated thinning can increase tree growth by as much as 30%. The problem with thinning is you can't be sure you've made the right decisions until you harvest the forest 15 to 20 years later. If you could only build a model forest. At Yale University, Professor Ken Mitchell has been trying to do just that, using a computer. Mitchell fed into a computer statistics about how well Douglas fir trees grow under different conditions. If the model accurately reproduced the growing patterns, this could aid in maximizing timber production.
There may be 10 ways in which we can thin a stand. And so we can test each of these methods on the computer, and the forester can look at the results, and what usually happens is that he can see that something isn't good. It's obvious in retrospect, or it's obvious after he sees the output. It confirms what he knows intuitively.
Mitchell wanted his model to be more than a hypothetical one, so he based it on a real forest. He arranged to have aerial pictures taken of Douglas fir stands. But ordinary aerial photos wouldn't be good enough because Mitchell needed to determine the heights of the individual trees. This strange torpedo-like object is a three-dimensional camera platform developed specially for this project. Still cameras located at each end of the 16-foot tube take pictures simultaneously. The photos must be taken from a fixed altitude of 200 feet so they can be precisely analyzed later. The location and height of each tree in the forest was carefully plotted and converted into computer coordinates. Mitchell's printout looked like the real forest seen from the air. Each tree in the computer forest was assigned a number. These trees were 8 years old when first plotted. According to the photos, they were about 8 feet tall. Mitchell then had the computer grow the trees through their natural cycle and thin them every 3 to 5 years. These are the trees at 17 years, and then after more thinning. Tree number 54 seems to be growing the strongest and is being favored by the computer. At 29 years, this Douglas fir was almost 70 feet tall and on its way to maximum growth. But how can Mitchell tell all this just by looking at the tops of trees?
Lately, there has been increasing interest in the crowns of trees because it's the crown that intercepts the light, manufactures the carbohydrates, and eventually the wood. So it's in the crown is where the action is. The crowns of trees compete with one another for growing space.
The key is looking at the forest from the right point of view. Not all computer programs are for managing the forest. This is the Sunstuds Incorporated lumber mill in Roseburg, Oregon. Here, the saw operators have been replaced. Every sawing decision in this mill is made by a computer. The computer measures the overall diameter of each log. It then quickly decides where to begin cutting. Even the natural irregularities are taken into account. This 200-year-old hemlock will be cut into 250 2x4s in less than 1 minute. Sunstud's mill now gets about 20% more lumber from each log just by making the right cutting decisions. With the number of big trees rapidly diminishing, the full use of each log has become an absolute necessity. In every lumber town, the sky used to be filled with billowing smoke from the sawdust wigwams, burning mill waste. No longer. Today, sawdust itself has become an important resource. It's now being used as fuel to heat steam-generated electrical plants. These frequently provide the energy to run the nearby sawmills. New technologies have refined the making of wood products to an art. 2-ton logs are spun like matchsticks and peeled paper thin for plywood. Until the mid-1950s, nearly everything was made out of solid wood, but this is becoming a luxury today. Yet this new, more efficient and less wasteful use of lumber in composite form has actually increased the market for wood. The U.S. Forest Service has conservatively predicted that by the year 2000, the American consumer will double his current demand for lumber. But we also use forests for recreation and to control water runoff from the rain, and as protection for wildlife and fish. How are we going to manage this so-called renewable resource to meet all these demands? Forestry professor at the University of California at Berkeley, Henry Vox.
What we do in the next 10 years in the way of increasing the level and extent of forest management, whether it's for timber growing or for recreation or wilderness purposes, has a big effect on what will be available 30, 40, 50 years from now. And if we don't start quickly in the next decade to make the investments that we need, then there's going to be far, far less of these benefits available in the future than might otherwise be the case.
This urgent need for immediate long-range planning is not lost on the lumber industry. The chief scientist in charge of the Weyerhaeuser Company's forestry research is George Stabler.
We've not yet scratched the surface on our ability to grow and manage and maximize the productive potential of our forest lands. That's because we've been concerned up till very recently with harvesting the old growth resource, the forest that the first settlers found here, a nature-given resource in which we had no hand. The next forest being managed will be vastly more productive than this old forest.
The lumber industry has been going to great effort to duplicate in the Northwest the success of the Southern Tree Farm, with Weyerhaeuser leading in scientific research. This is their plug seedling nursery in Rochester, Washington. In these greenhouses, technology is being used to mass-produce Douglas fir trees to be cut after the year 2025. The Douglas fir seeds are dropped into tubes filled with rich topsoil. Each carton contains 200 tubes, and each must be carefully checked. The naturally brown seeds have been dyed a deep green so they can be easily spotted against the soil. A protective covering of porous rock on top of the seeds completes this first stage. In each 8-hour shift, 100,000 Douglas fir trees are planted. These Douglas fir seedlings are 5 months old. On each side of these greenhouses, there are 1.8 million seedlings. Almost 12 million infant Douglas fir trees are growing in this one location. Each day, the seedlings are watered and fertilized. A small army of gardeners prune the new sprouts, 2 shifts a day just to keep up with the task. In the year 2025, when scheduled to be harvested, these trees will be over 125 feet tall. It's critical where these seedlings will eventually be planted. The seeds must come from similar terrain and climate if they're to grow successfully. Seeds from 2,000 feet in elevation will not grow at 4,000 feet. every container must be cataloged. When they reach a plantable size, around the 9th month, the small trees are prepared for shipping. An operation of this nature is phenomenally expensive. National cost estimates for replanting trees run from $30 per acre to $200 per acre, depending on where one's planting and how effective they're trying to be. In the mountainous Northwest, the costs tend toward the higher figure. These seedlings are to be planted on Weyerhaeuser's own land. Once bundled, these trees aren't headed for planting just yet. They're wrapped to retain their moisture and put into cold storage. The planting season for the Douglas fir is a brief 3-week period in October before the first snow. This greenhouse operation runs throughout the year to store enough trees. And then come October, the planting begins. One quick poke in the ground and each tree is ready to grow. In mountainous terrain, it must all be done by hand. Planting seedlings this way dramatically cuts down the amount of time to establish a new stand, and it's much more effective than scattering seeds, which are quickly eaten by animals or blow away. This kind of large-scale intensive planting only began in the Northwest in 1966. Last year, Weyerhaeuser planted 178 million seedlings on its own land, over 1/3 in the Pacific Northwest. A densely planted acre of these Douglas fir trees should produce as much or more wood in 50 years as a natural acre of big trees which have grown hundreds of years. Weyerhaeuser scientists hope their seedling trees will grow as well in natural situations as they're doing in this test acre. Even under controlled circumstances, mature Douglas fir trees only produce a good crop of seeds every several years. At the Oregon Graduate Center in Beaverton, Oregon, research is now being done which may produce tomorrow's seedlings. This is Dr. Tai Cheng. Dr. Cheng is trying to eliminate one of nature's most time-consuming steps, growing seeds. What Dr. Cheng is trying to do is reproduce trees without seeds, to mass-produce trees from small bits of tree tissue. Everything, including the pine needles, must be sterilized. To begin the experiment, Dr. Cheng sliced a single needle into sections and then embedded each section into a clear layer of growth hormones. She placed the entire tray in an incubator flooded with artificial sunlight. After several weeks, the needle sections exploded into shoots. Every tree cell has all the basic genetic characteristics of the entire tree. Each of these shoots should also have all these genes. Now Dr. Cheng is trying to produce roots on these cuttings. Again, she's adding growth hormones. If roots sprout successfully, if this next step works, Dr. Cheng could conceivably mass-produce superior trees without seeds and without pollination. There are some future problems yet to face, especially how to deal with the fact that these trees are all genetically identical, which means a disease or insect infestation might easily sweep through an entire forest of these trees. But the immediate problem is making it work at all. Growing the seedlings is still only the first step in farming trees. Growing them commercially in the mountainous Northwest is another problem altogether. For what grows well on one side of a mountain may be entirely different from what grows best on the back side. Species and growth rates vary widely. These differences are especially pronounced in the Cascades, where the western slopes are drenched by clouds rolling in from the sea, and the eastern slopes are relatively dry. This is Dr. Jerry Franklin, Chief Plant Ecologist of the Forest Service's Pacific Northwest Research Station. The U.S. Forest Service has been surveying these differences on the nation's forest land for the last 50 years. Franklin wants to determine the tree's age, to know just how long it took to grow this tall. Assessing an acre begins inside the tree. By counting the tree rings, Franklin found this Douglas fir growing in Oregon's Grand Valley to be 110 years old. Measuring the girth of the tree tells Franklin how fast the tree put on new wood each year, and also indicates to some extent the moisture and nutrients available in the area. At 30 inches, it's relatively small for its age. The last measurement is a very accurate scaling of the tree's height. The tree is 109 feet tall.
And from the height and age measurements, you can determine what the site index is of the forest. It is a good relative measure of productivity of a particular area. Now, this particular forest stand would probably run around a Site 4 or low 3 on a 5-class system of site index, where 1 is the most productive forest land and Site 5 is the least productive forest land.
Appearance can be very deceiving. This green area is slightly below average in its tree growing ability. Site indexes now used throughout the United States measure how well trees grow in a particular area, but not how easy it is to get new trees started. Nevertheless, some important generalizations can be drawn.
Now, when you get on a very productive site, typically temperature and moisture are quite favorable for establishment and growth. And what you have to watch out for is the light factor, competition from other vegetation. In the case of the very cold site or the very hot, dry site, what you've got, of course, is either temperature or moisture, both limiting. And when you are on a site of that kind, where one of those two factors is a major constraint on seedling establishment, you have to look much more carefully at the cutting system you're going to use.
There are basically 4 methods of harvesting timber. They all have different effects on the land's ability to regrow trees. The oldest one, called selective cutting, is just that, selecting the biggest trees and cutting just those trees. This type of harvesting is barely visible to the untrained eye. The second type of harvesting is shelter wood cutting. The trees are gradually removed in several stages, leaving some trees to provide natural protection for the remaining forest. A third method, called seed tree cutting, removes all the trees except a few, usually the best, left to naturally reseed the area. Gusting winds sweeping across these open sites frequently blow down all these separate trees. The fourth method, the one used most often today by the lumber industry, is clear cutting, where all the trees in a large area are removed. Every tree, no matter what size, is cut. "60% of all industry harvesting done today is by clear cutting. Quite simply, it's the most efficient and most economical way to get trees off the land. One needs fewer roads and less equipment to harvest an area. There is much controversy surrounding clear cutting. Industry argues that clear cutting is necessary to meet our constant demand for wood. Environmentalists charge that it's ecologically unsound, especially because it's used on all types of terrain. The question has been raised whether it might be illegal on the national forests where it's used extensively. Conservation groups are quick to point out how ugly it is. Some clear cuts in Oregon and Washington run from horizon to horizon. If trees are to be treated as a crop, is clear cutting the best way to prepare the field? This question cannot be taken lightly because clear-cut landscapes dominate the Northwest, and some are very large. This is a satellite photo of snow-capped Mount Hood and the surrounding mountain range. The white spots are not housing developments. They're clear-cut patches on the forested mountainsides seen from 570 miles up. Obviously, clear-cutting causes a radical change in this once virgin land. How this change will affect the land's future productivity is a major question confronting forest managers. It rains in the Northwest more than 160 days a year. A lot of moisture falls on those clear cuts, yet little research has been done on its effects. Scientific studies of forests are much like trees. They take time. One long-time study in the Northeast has some significance here. This is the Hubbard Brook Experimental Forest in New Hampshire. In conjunction with the Forest Service, a number of university professors and students have been doing research here since 1963. At Hubbard Brook, the natural forest was measured, marked, and examined right down to almost every leaf. This area couldn't be better suited for studying water flow. Just 5 feet below this topsoil is solid bedrock, so any moisture hitting the area will run out at the bottom of the hill. 10 years ago, a section of Hubbard Brook was clear-cut and new measurements were made. One of those working on the project was Cornell professor Gene Likens.
All the trees were cut down but left in place. No logs were removed. And then for 3 summers thereafter, herbicides were used to prevent any regrowth of the vegetation in the area. And we found from that experiment that the amount of water draining from the system was greatly increased, but surprisingly we found that the amount of nutrients going with that water was vastly increased.
The nutrients are what makes the soil fertile. Even when foliage was allowed to return on the Hubbard Brook hillside, the nutrients continued to flow out at a higher rate for several years. Could this nutrient loss seriously hamper future tree growth? This is the Mount Hood National Forest in Oregon. This area was clear-cut 19 years ago. One of the several uses of the National Forest is to provide timber for the nation. From these forests comes over 30% of our total wood supply. The year following logging, this area was replanted with Douglas fir, and the Forest Service now considers it adequately stocked. But the growth has been quite uneven, and many of the trees in the flat have died. Why? A clue lies in this stream, which drains the area. Geology professor Bob Curry from the University of Montana spotted the change.
This algae represents the nutrients that used to be in the forest soil. This is the lifeblood of the forest soil. This algae formed because nutrients were carried away from the forest soil following clear cutting. Because the water course is opened up, because the forests have been cut away from the water course, the water temperature has gone up, the light penetration has increased, and that causes the algae to be deposited and to form and grow here in response to the forest soil nutrients.
In the living forest, nutrients cycle up through the roots into the tree and then fall back to the ground in the leaves or needles. This is a closed loop. Logging breaks this loop. Recognizing this as a problem, some lumber companies have taken a hint from agriculture: fertilizer. Nitrogen pellets are sprayed on both established and newly growing timber stands, usually at 5-year intervals. In the newer stands, these added nutrients have caused a 20 to 30% increase in growth. But the long-term effects of these concentrated dosages on forest environments are as yet unknown. In any case, this is an expensive operation, and only the larger corporations can afford the investment. During logging, the future productivity of the land is also affected in less subtle ways. On clear cuts, where the slope's not too steep, it's standard practice to use giant tractors for speedy log removal. Yet even on the best managed, most carefully planned operations, the sheer weight of these machines has harsh effects on the ground. The soil is crushed and changed. Tiny air spaces essential to good moisture and nutrient circulation are squeezed away. As much as 1/3 of the land's future productive potential might be lost because of these operations. Other hauling methods do far less damage. This is high lead yarding, where logs are pulled out by cables. It's generally used on the steeper slopes. The main problem is it's much slower than tractor logging. New logging techniques are being tried which could become absolute necessities. This certainly causes no major ground damage. Helicopter logging is still mostly in the testing stage. Its future use is unclear. In theory, it works and is good for the land. But it's incredibly expensive, almost 20 times as costly as tractor hauling. For companies working on a small profit margin, it's not very attractive or practical. Caring for the land costs money. When one doesn't care, the results are devastating. Too many roads, too little concern, cutting costs here and there, and a clear cut looks more like a war zone. The odds of anything growing back here are small. The clear-cutting controversy is far from settled, even in the science community. A major debate centers around the Douglas fir seedling and what it requires to grow best.
This is a Douglas fir seedling. With fertile soil, plenty of rain, and lots of sunlight, it's a fast grower. But in the shade of a neighboring giant, it doesn't have much of a chance. That's why we must harvest in sunlit blocks instead of cutting a tree at a time here and there.
Just a minute. Sunlit blocks? What's the scientific thinking behind this statement? Weyerhaeuser's chief research scientist, George Stabler.
We clear-cut the Douglas fir because it's an intolerant species and does not grow well unless it has an abundance of light. And to get this light, you have to clear off all the trees and start a stand evenly, so the trees all come up at the same time and all have access to all the light that's available.
The Douglas fir does indeed need an abundance of light, but this point of view implies that clear-cutting should be done wherever new stands of trees are to be replanted. Is it necessary to completely clear a mountainside to regrow Douglas fir? One who feels quite differently is Jerry Franklin of the Forest Service.
It's important to recognize that very few species actually require clear cutting as a condition for their regeneration. You often hear it said that it's necessary to clear cut Douglas fir because it needs full sunlight. And the fact of the matter is quite to the contrary. It is not necessary to create large clear cuts to reproduce Douglas fir, insofar as the ecological requirements of the species are concerned.
Why then do some hold such an opposite view?
Nature has perpetuated these species by clear-cutting them by some catastrophic means. And this may be fire, it may be an insect epidemic, it may be a windstorm, a wind throw, where all the existing trees are cleared off. Now you've got lots of light on the land, and you've got and the tree is capable of regenerating itself and growing thriftily under those circumstances.
It is not a duplication of natural process. It's not even out here in the Douglas fir forest, because Douglas fir originally reproduced under a condition that was much more like a shelterwood system than a clear cut. That is to say, after a fire, you had a lot of standing snags, casting shade, a lot of down material, a lot of standing dead, and this produced a very moderate environment. The classical experiments that were done with Douglas fir, which seedlings were growing under various intensities of shading, show that it can reproduce very well under partially shaded conditions. As a matter of fact, reproduces better under a partially shaded condition than it does under a completely open condition.
With some help from man, Douglas fir will grow in a clear cut, especially on the more productive sites. But the conditions are far from ideal. Manager of Crown Zellerbach's managed forest, Frank Deckebach.
You're looking at an area here that was clear-cut approximately 6 years ago and immediately planted the following winter season. There, a series of problems have come upon us since planting of the Douglas fir of the type that you see here. The young trees have been growing since planting, but we find that with the Douglas fir, it has a slower early growth and has a problem with competition from fast-growing hardwoods such as the big-leaf maple that we see in the big clumps across on the far hillside.
The sun-loving trees overtop the planted Douglas fir and cut off the sunlight, which in turn stunts their growth or causes them to die.
We are now using the helicopter for aerial application of herbicides, these herbicides are selective in that they will kill the hardwoods but not damage the Douglas fir.
There's no research yet on the long-term effects these herbicides will have. The spraying just began recently. But what if the Douglas fir needs these companion species to survive? What if nature's scheme is best? Despite all these knowns and unknowns about replanting, the timber industry will continue clear-cutting because it's the most efficient way for them to remove logs from the land. Whether it's the most efficient way to prepare the land for a new crop is still in question, and not all clear-cut land is replanted. From the moment an area is clear-cut, each step towards getting the land back into tree production costs money. The research, the new materials, the manpower and machinery. Who can afford to replant? For the forest industry, which needs the wood to feed their mills, the investments to replant their own lands are absolutely essential. Even if all this land is replanted, which to date it isn't, it won't be nearly enough to meet our projected future demands. The industry is the first to admit this. The desires of these 4 million private landowners are mixed. Those who do sell their timber make their money from the trees, not from milling or manufacturing. And why should they replant their lands? The next crop won't be harvestable in their lifetime. One solution is to have the U.S. government lease some of these woodlands to assure full wood production. But ironically, right now there are over 3 million acres of national forest land which have been cut and never replanted. Despite the fact that selling national forest timber brings high income into the U.S. Treasury, Congress has never voted sufficient funds for reforestation of this public land. The economics of tree farming may be the single most important factor in deciding if trees will be a renewable resource. Forest economist Henry Vox.
Certainly all land can regrow trees, but the question of cost is terribly important, and the most important aspect of cost is the interest on the capital investment that's made in the timber growing. The capital investment to establish a stand of timber, new plantation, is substantial, perhaps $100, $200 per acre. Then that stand must be held 40 years, 50 years, 80 years, 100 years before the trees can be harvested. And during that period of many decades, interest on the original investment is, of course, a part of the cost that has to be met.
The renewability of this resource doesn't come cheaply. At 7% compound interest, a $100 investment in replanting trees held for 100 years equals $86,770. That amount must be added to the final price of the wood just to cover interest rates. Higher per acre costs, higher interest rates, and the long growing periods for trees will make the future price of wood skyrocket. But if the investments aren't made, then trees fall right back into the category of mined resources like coal and oil. Even if we can afford to replant trees, and even if we continue to develop the technologies to do it, there's one problem which could mean this whole scheme won't work at all. It concerns the forest soils and the long-term effects of repeatedly harvesting tree crops. Geologist Bob Curry.
soil is not the same kind of a renewable resource that trees are. The soil resources have different limits upon them than do the forest resources. In most forested sites in western United States, the soil profiles which support our forests are geologically young. By young, we mean 10 to 20 to 30,000 years of age.
When trees are completely removed, they take away maybe 15 or 20% of the soil nutrients. This may be more than can be replaced by fertilizing, and this is what worries Curry.
It's true that if only 20% of the nutrients are lost per cutting cycle, we can get at least 5 cutting cycles. But if it takes many thousands of years to form these nutrients, and the cutting cycles are at most once every 100 years, we have a finite life to this soil resource. Yes, we're forming nutrients all the time, but we are taking them away faster than we are gaining them. Through repeated cropping of the trees, repeated misuse of the forest and soil resources, we can utterly lose the productivity of the land.
When will we know this for sure? Not until long after we're committed to tree farming as our main source of wood. It will take many cutting cycles to fully understand the effects of clear-cutting and managing forests. Trees do grow, do renew themselves, but do they grow on a timetable that will meet man's needs? Right now, the natural old-growth trees are the backbone of the lumber industry, but they won't be available for lumber much longer. Either they'll be held aside in wilderness areas or parks, or they'll all be cut down. We must make hard and careful decisions about how to use them now if we want them in the future. To exploit trees as a renewable resource, we must grow them as a crop, like corn or wheat. But is this possible? It's ironic that we probably won't know the answer until all the natural stands have disappeared.